So I hit the record button, Merve. I am passing the ball to you and muting myself.
Sure. Thank you, Tansel. Hi, everyone. Welcome to today's Forum on Control Robotics Engineering Seminar. So, as always, I will talk about the FoRCE little bit. FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities around the world. Thus, Tansel and I periodically invite distinguished people like Dr. Valasek to give their talks on recent research results related to robotic and control. The aim of the FoRCE connecting academicians and government industry researchers together through the research and education discussions. So we cordially hope that you will enjoy all the FoRCE events and you will find them highly valuable for your own research. By taking this opportunity, I also would like to mention about the support from IEEE Control System Society, where you can also find the past FoRCE talks and many other talks at the IEEE CSS video library webpage. Also, I'm going to talk about the WebEx a little bit. So you will be all muted during the presentation. If not, please mute yourself. And if you want to ask questions after the talk, you can do it by simply unmuting yourself, or you can post your questions to the chat box. And this session is going to be recorded and to be posted for the FoRCE web page as well as the IEEE CSS web page. So jointly with Tansel Yucelen, we are very proud today to have John as a speaker, and I will shortly talk about John's bio. John is Director of Vehicle Systems and Control Laboratory, and he is a TAMU Professor of Undergraduate Teaching Excellence. He is Professor at Aerospace Engineering and member of the Honors Faculty at Texas A&M University. He has been actively conducting autonomy and flight control research of manned and unmanned air vehicles in both industry and academia for 35 years. John is a fellow of AIAA, senior member of IEEE, chair of the AIAA Intelligence Systems, TC, and associate editor of the journal Guidance, Control, and Dynamics. John earned his Bachelor of Science degree in Aerospace Engineering from California State Polytechnic University and Master and PhD degrees in Aerospace Engineering from the University of Kansas. So for all of you who are here, I would like to thank John for participating in our forum as a speaker. I believe, John, you have the presentation ball, so please go ahead and start whenever you are ready. Thank you.
Very good. Thank you, Dr. Dogan and Dr. Yucelen. I really appreciate it very much, you inviting me to speak. The presentation I'm going to give, you see the title right there. I'm going to include work that my former PhD student, Anshu Narang Siddharth, contributed to this, former PhD student, Dipanjan Saha, and current PhD student, Christopher Leshikar, because this is going to build on it. I'm going to actually do some of the earlier work that builds on this, because we did full state feedback in the earlier work. We're doing output feedback in the current work. So you need to see how that develops and goes through. For the agenda, we're going to follow the theory, computation, experiment paradigm. And I will say for this that I'll do some theory on standard versus non-standard form. That's very, very important to what we're doing. We're going to be addressing only the non-standard form. So I'll talk about what that is. We're using geometric singular perturbation theory to make it work. So that's the linchpin of which it's all based upon. And we'll talk about state tracking then with output feedback, which is, again, a very interesting case we're doing now. For the two examples, I'm going to do one very small second order regulator system, non-standard with 2 time scales to show the basic approach. And then for the bigger example, I'm going to show an F-16 maneuvering using output feedback. Eventually, we'll be doing the experiment. We have flight demonstrations planned. We're not doing those yet. So I'm not going to show you today any hardware experiments. We're working on those now. I'm going to stick on the theory and the computation side, but we definitely are going to be testing this in hardware. Okay. I want to recognize my student research team. This is our 25th year and of having them and everything. This is our fall of 2019 picture. This is pre-COVID. We've not had a picture taken in 2 years, everybody, for this. So several of the students on here have graduated, several undergraduates who are now graduate students, but I want to thank them. These are the people that, you know, work at the sharp end of the stick and get the really heavy lifting done. So thank you to them. The 2 time scale systems that we're going to look at, I'm actually going to look at multiple time scales, but we'll start with 2 time scales for some examples we're familiar with. I can have linearly damped oscillators that are going to have an exponential envelope that's on this, and then I'll have some oscillations that sit within that envelope on that. So there's two time scales there that are going on. Flexible beams will definitely have two time scales if I have higher order bending modes and things like this. So fast and slow for doing that. In aircraft, which is kind of what we're going to be focusing on right now, the typical of two longitudinal modes that are very widely separated in time scale, phugoid, which is low frequency, low damping, and then short period, which is high frequency, high damping. And they of course exist all times for that, and they're very widely separated in time scale and in amplitude. So the example you're seeing here in time scale separation is this is a McDonnell Douglas A4 Skyhawk, but you're seeing in velocity, you're seeing here that the short period is already going through its oscillation and damps out to steady state in the first 10 seconds. And then the slow state on this, the phugoid, keeps going on for more than 100 seconds. So this is, again, it's showing particularly for an aircraft example, these two time scales are going on. I have modes that are widely separated, and that's kind of what we're after. If we consider, I'm going to work on the aircraft problem for right now on this. We're not going to do like enzyme kinematics and things we've talked about in the past. If I look at this, and you see the typical F-35 here, modern high-performance aircraft, there's the dynamics that I have. And in the basic sense, they're going to be nonlinear from that. And I'm assuming that they're affining control, because that'll work actually quite well for an aircraft problem. If I go to now something like on the right-hand side, and you see this, I'm going to have like a morphing surface that's right here. This, and that's an animation that's having trouble playing for that. This will then have, oh, PowerPoint killed. Let's go back to it. Okay. Am I sharing still, or did it lose that?
Oh, not yet. So you were sharing.
Good. Okay. So let me put that down to go back to that. So I get my screen back. I think it lost it again.
There should be share button on the control bar.
That's not it. Okay, are you seeing it now?
Not yet.
Not yet. Share it this way now. How about now?
Yeah, perfect.
Okay. So if I have a system that's going to have many, many degrees of freedom in it, and hopefully this is not, I'm going to get past that animation that's causing the problem. We're going to go past that and just keep going with it, okay?
Yeah, animation again killed the presentation.
Yeah, I'm going to skip past that part because it's the only animation that's in the whole thing, really. Okay. So, yeah. Okay, so when I do that now, what I have to deal with, I can have non-affine control, I can have nonlinear control distribution functions and such. So the issues that I have here, typically you're seeing on the left-hand side, the one I'm going to focus on is multiple timescale behavior for this. And common solutions to all those problems are to use gain scheduling, offline control, typically pre-computed, and a lot of times linear system representation. So that's not bad. You can make it work. It's been done for many years. But there's some nicer things you can do if you're not just going to be doing a linear system. The air vehicle applications, there's many for aggressive maneuvering, hovering of a helicopter, approach and landing, the propulsion controlled aircraft, and of course autonomous soaring, which is the first example, the first problem that was tackled that we did, which led to doing all this. Okay. Now the theory side, let's talk about standard versus non-standard singular perturbation methods on this. So Peter Kokotovich and Christofides in 1996 were working on the standard singular perturbation method. So what that means is X are going to be the slow states, Z are going to be the fast states. And I'll have the singular perturbed parameter epsilon, which has a value between 0 and 1, will be multiplied on Z dot there. So when I divide both sides by epsilon, now I have the right-hand side being multiplied by a large number. And that epsilon is what's separating the timescales and distinguishing between fast dynamics and slow dynamics. The typical way to solve that is to say at some point then we're going to assume that epsilon is equal to 0. And now what happens on the right-hand side is I still have the slow states evolving, but the fast states are now not longer a differential equation, they're an algebraic equation for this. So what you assume for the standard system is you have unique real roots in some domain, and typically, most of the time, the results in the literature neglect the coupling between the control effectors and slow dynamics. So you get only approximate bounds. When you do the non-standard method for that, you're saying I don't have a unique real root for that. I have infinite manifolds, or many manifolds may exist, and there is nothing in the aircraft literature prior to what we were doing that we're really doing the non-standard. And then Friedman in 2001 started really tackling optimal control for regulation of the states in the non-standard. You can break these down into two different categories here for the standard systems on the left, as you're seeing. If I have that where I have fast dynamics that are linear in the fast states, and that's the typical thing to do, there's many works that you can see. Tikhonov back to 52, and all kinds of people much later than that and are still working on it. Now, it says there that it's not applicable to aerospace. It is if you are going to make some assumptions and make some simplifications, but it's not the best one. For non-standard systems, the nice thing to do about that now is you leave the fast dynamics as nonlinear. You're not linearizing the fast dynamics because you don't have to get those isolated roots on that. You leave it nonlinear and just handle it that way. You're going to use manifold invariant theory on geometric singular perturbation next. So that's when we started this and everything was to go after nonlinear, non-standard, and our work in 11 and 12 and 14 was doing that. I want to mention and give credit to Peter Kokatovich, Hassan Khalil, and John O'Reilly. This book is spectacular. It's a classics on this. So much of the work that was done that you're seeing in the literature right now really forms the basis for this. So I need to definitely recognize this book. I recommend it highly. That's looking at standard versus non-standard. If we look now about where the gaps in the applications are, the gaps in things doing, I can look at these by on the left-hand column and saying linear and nonlinear, standard, non-standard, and such, as you can see there. And on the right-hand side, those columns are talking about asymptotic stabilization and slow state tracking. There's been a lot of that. Simultaneous tracking of slow and fast states. There's been a lot of it for linear and nonlinear, but for the nonlinear standard with multiple isolated roots, not really anything in the literature that I can see. We did in 2012, on the bottom of the third column, we did for the nonlinear non-standard, and that was full state feedback. And what we're tackling now is the output feedback, and I'm leaving those as dashed. We're going to go after, what I'm going to show you are results that we're after this column right here, output feedback for nonlinear non-standard systems. But for everybody out there working on these, researching these, this is wide open to be able to do it for the systems pretty much. Okay. Now, what we're doing is to break this into 4 time scales in our earlier work. This is the feedback, the full state feedback, which I'll then show for output feedback. And what you're going to say is X are going to be the vector of the slow states, Z are going to be the vector of the fast states. I will then have delta 1, the slow actuator states, delta 2, the fast actuator states. And I'll have the epsilon, of course, lying between 0 and 1. So here's what I have. I have the dynamics now for the slow states, dynamics for the slow actuator, fast, and then fast actuator. And you can see what's going into what. This U1 is going to be the control law that's going into the slow dynamics, or the slow actuator, sorry. The U2 is going to be the control law that goes into now the faster actuator to do this. And then the actuators themselves, the delta, not delta 1, delta 2, they're going into the fast dynamics. And notice that again, same thing into the slow dynamics. So it's a very coupled system. And our objective is just to track a slow state, and this is the early work for slow state only, track a slow state reference as it goes to some reference condition as time goes to infinity. The nice thing about this and what we're going to use is going to be based upon work done by Fenichel in 1979. And here's basically how this works and the nice properties you get about this. On the left-hand side, I have derivatives with respect to the slow time scale t that you have. So there you have x1 dot minus x1 minus z, x2 dot minus x2 minus z, and then there's the fast dynamics. If I set epsilon is equal to 0, notice what happens from this. Now what I have is the slow states, the slow dynamics will still be evolving, and the fast states have already settled onto their manifold. That's why they're 0. They've already settled out. So on this, the slow subsystem is saying slow states evolve, but the fast states have already gone steady state to their manifold or to their equilibrium point. Okay. On the right-hand side, you're going to say with respect to the fast time scale, notice what happens now. Now when I take derivatives with respect to that, the slow states are at 0 and the fast states are going to evolve. So what that's saying in the fast time frame, the fast subsystem for this, the slow states appear to not even start yet. They're still basically at initial condition of 0. They haven't even got moving yet while the fast states are doing their thing. So that's how this separates out very, very nicely. The bonus that you get is you get a reduction in the order of the system. You're going to have a reduced order subsystem. We talk about this a lot. So on the left-hand side, notice now I've gone from a third order system down to second order because Z is now going to be at 0 for that. So one thing about cursor dimensionality for this is you're not really going to have to worry about that, because if I have a 10th order system, I'm still going to have fewer orders based upon how many timescales that I have. So this does not blow up that way. You're still going to stay lower for that. So it's nice. It's going to be nice. It doesn't mean you have no problems, but I'm not going to have the cursor dimensionality hitting me on this when I go to higher levels, because again, higher orders, because I'm going to be subsystems that are going to be reduced order. Now, the whole assumption on to do this and everything is to say, does the slow system approximate the behavior of the complete system? And the answer to that will be yes, based upon Fennichel's work, provided the fast subsystem is stable about the manifold. So here's what it looks like graphically. The same complete system, slow and the fast, you're seeing here on the previous page. But what this is showing then is in X1, X2, and XZ, so in 3 space on this, you're seeing that the fast dynamics are going to go to their manifold very quickly. And then you're saying that the slow subsystem is going to be essentially what's going to be representing the behavior of the system. Now, I need to say this is very important. What does the geometric property buy you on this? The geometric property buys you something very nice. And that is that in the work, if you're going to be doing it with asymptotics, you have to have isolated roots that are showing up on this. And that's what a lot of the limitations on using the non-standard form, because the non-standard form, I'm not going to have isolated roots, right? Because I have a nonlinear dynamic on that, a nonlinear system, and I don't have roots for that, even though they're going to be multi-roots, okay, for doing that. When I use now geometric singular perturbation theory on this, now what I have are invariant manifolds. And now the invariant manifolds are not going to be having that problem on that. The invariant manifolds are going to account for multiple non-isolated roots. And the neat thing about it is I'm going to get to the same place. The equations that I'm going to use doing the geometric and the equations I'm going to use using traditional asymptotics will both converge to the exact same equations, but the assumptions and limitations you did to get there are going to be a bit different, and they're quite a bit nicer when you go through the geometric route to do that. Okay, so that's why we did the geometric work for that. There are 2-stage designs and controls. There's a lot of work that's been on this. I'm going to just basically say very, very fast to go through. The one thing I want to point out here is the middle one. The work that Anshu and I were doing early on was to approximate the manifold using center manifold theory. And it was very difficult to approximate the manifold. It took a ton of work, and we could only get bounded tracking for that. And because of that, here's now the big idea that's going to come out of this as to what to do. And here's the following. I have my original system. I'm going to put it into air coordinates, same system I just showed you right there. I have to worry about the analytical construction of the manifold. It's not possible, okay? I don't have knowledge of the explicit timescale separation parameter, that epsilon, not every time. For simple systems, it's not bad, but for sophisticated systems, it's very difficult to be able to get that. For an aircraft system, very hard to get that, and a lot of work goes into just getting it for one operating condition. And the other issue here is not all actuators are fast. You have a mix of slow and fast on many systems. So our approach then is to now include the fast states as in the design as an additional control variable. So here's the big idea. You're not going to calculate the fast manifold like we were trying to do before. You're going to specify it. Okay, so this is exactly like designing a control law using, Lyapunov theory. You don't design a controller and then analyze it by constructing a Lyapunov function to check stability. You can do that. The better way is to say, I'm going to pose this Lyapunov function that I have, and then ensure that my control law will make sure that the derivative of it is negative definite. Okay, so that's where the inspiration was to do this. Quit trying to calculate the manifold, specify it within these conditions that are going to do that. The nice thing that happens on that now, the non-standard form becomes the closed loop standard form. So this is very, very important to point out. Our work is not creating a whole set of theory for the non-standard problem. We're not doing that. What we're doing is we're taking the non-standard problem and properly done with feedback, we're converting it to the non-standard form. The non-standard form has been solved using many techniques for a long time. So what I'm saying is properly using feedback and doing things with the dynamics, you can convert it to the standard form in closed loop. That's what we're doing. And we want to have the approach independent of the perturbation parameter. I don't want the gains or the compensator to be a function of epsilon for that. Very, very important to do that. So the way you do this in the 3 steps is you're going to determine the slow controls and then the fast dynamics, the manifold. So the zero superscripts are meaning manifolds on this. So I'm going to stabilize the slow subsystem, assuming those are manifolds. I then will determine the fast actuator manifold and then the fast control law U2 for that to stabilize the fast subsystem about the manifolds. And then finally, I'm going to verify the interaction conditions on that to ensure properties carry forward. So what I'm really doing here is I'm using the fast dynamics, the fast manifold, as a control input to the slow dynamics. That's a key part. That's what's making this work to be able to do it. Okay. And when you go through, just basically, this is just showing the approach. This is the full state feedback. I want to get to the output feedback. That's quite a bit more interesting. What you're saying now is I'm going to asymptotically stabilize with errors on this at E is equal to 0. So on the left-hand side are the dynamics that you're seeing here for the slow dynamics. So here's the slow state dynamics, the slow errors, and then the slow actuator. Notice that the fast dynamics and the fast actuator are already at 0. So these are the same equations I showed you before when you're setting E is equal to 0. That's the same thing. So I'm using, at this point, I decided to use Lyapunov functions for this. You can use Lyapunov, whatever you want for this. Lyapunov is quite convenient for this, as you all know. So I'll do a Lyapunov function V of TE and design the actuator for it. I'm going to get uniformly asymptotically to stabilize it. I'm going to be having it then below some bounds that are on this. I'll do a second Lyapunov function to design the control going into the slow one. So again, to stabilize this, nothing super duper here. I'll go to the fast subsystem now, and now you see, of course, the errors in the slow states are 0 and the actuators are 0. And what I'm now looking at are the fast errors and the fast actuators for this. Again, a Lyapunov function for the design a manifold for the fast manifold for that, fast actuators, uniformly asymptotically stabilize it, and another one then to do this for, pardon me, the fast control law U2 to do that. Okay, so you put those together, and now what you're going to do is you're going to say, I have to bring all these together and do this. So to be honest, you need to use a composite Lyapunov function, and that's what I'm going to show next to be able to do that. I have to have the effects of the deviations between the complete reducer subsystems that occur. Number one, making that assumption that it's stabilized between the fast states and the actuators while stabilizing the slow subsystem, the time-varying nature of the manifolds, and neglecting the singular perturbation parameter of the design process. So 3 different assumptions were put into this and conditions we're putting on, and we have to verify that. So what you're using now is a composite Lyapunov function for this, and of course you have to have negative definite on that. And all this is saying on this is stability analysis, and this has been proven in the paper, our ACC paper down there. I've got this big matrix K, and that's going, the size on that, the psi vectors are going to be errors between the fast states and the slow states. That's what that is a vector. The interaction conditions are the off-diagonal elements, because what I'm saying is by setting epsilon to 0, which it really never is in a real life system, setting epsilon to 0 and having these interactions, what's the price I have to pay? What do I have to do? And the interaction conditions are the off-diagonal terms. So with 4 timescales in this, slow dynamics, slow actuator, fast dynamics, fast actuator, this one came down to be then 16 parameters. I had to have 16 different factors in this K matrix, the off diagonal, to be able to look at. And so those are the conditions you work through, and it's not too bad. And we've proven that in there. So again, you have some bounds on this now to be able to start working forward and to do that. Okay. So this is now the computation part, and I'm going to show an example. There's 2 examples that we typically do when I show this. I'm not going to show the second one at all. I'm going to go right to that problem using output feedback. But let me say the first one will be the regulator in non-standard form with 2 timescales. It's a benchmark systems, and so it's an infinite manifold, so the GSPT does not exactly apply to it. And our control is going to convert the non-standard form into the standard form, okay? And the second one, I'm going to show that case to show the method. The second one I'm not going to show, we've used this also for a non-standard nonlinear F18. We don't even know what the timescale separation parameter is. The epsilon, you don't need to know it because our approach does not say you have to solve for it. Our approach says you're going to have bounds on it. As long as you're within these bounds, you're good to go. We're going to force the states to track a desired reference. We force a manifold to be exactly the fast state reference. So instead of saying the fast state manifold will be an equilibrium manifold, I'm going to have it be now the tracking system, the system that I want to be doing the tracking. That's what that'll be. We use a two-stage design, and I'll make no assumptions whatsoever where the nonlinearity appears. So I'm not going to show number 2, but I'll show number 1 in detail. So the system that I have is x dot is equal to z minus u. This is very challenging. This is a very specific system that is challenging because now the slow dynamics are only a function of the fast states. You know this, it's not x dot as a function of x and z, it's just a function of z. And there's the control appearing. And then for the fast dynamics, now they're a function of the slow states, okay, and the control. So this is very challenging to do, very unusual system. So the first step on this, slow subsystem stabilization, I design a manifold, Z for the fast states on that. Design the subsystem stabilization for the fast subsystem. There's the control for it very simply. I do the manifold computation, very, very simple one there. And the alphas are the design gains on this. And because it's all nonlinear, I want to stress this many times. It's all nonlinear. We're not linearizing anything on this. You're staying nonlinear the whole time to do this. And so with that, my manifold, I'm going to compute that, but that's good. My alphas are going to be design gains that I have, and there's going to be no graphical method or particular guidance for that. You just will know what bounds on what they have and then the signs on them. So there's the closed loop system there. I'm substituting that in, and notice what happens now. When epsilon is equal to 0, what have I done? I've now converted this problem from the non-standard form into the standard form closed loop. So I still have x dot is going to be equal to the development now. Now it's a function of the slow states. Alpha 1 and alpha 3 are design gains. I'll pick those. But notice what's happening on the fast system that's right there. I'm going to have 0. It's going to be 0 is equal to minus alpha 3 times the errors in z. So that's the whole point of this. Again, this is showing you're taking the non-standard form, converting it to standard form with feedback. But you have to be careful about how you do the feedback. To see what it does now, to how you can calculate this, epsilon star is going to be, when we calculate stability for this, epsilon star has this particular relation. So you can calculate it and say that's the value of that singular perturbed parameter that's going to be now where I'm going to lose stability with it. And remember, when epsilon is 1, the slow and the fast states are going to be the same. So I have x dot and z dot. But when epsilon is very small, it's going to be x dot equals z dot is equal to 1 over epsilon, 1 over a small number, and that's large, and that's going to make, that's how you model the fast dynamics to be much faster and such. So that epsilon is going to have a value in there. So you're seeing here a phase portrait plotted for different values of epsilon that's there. And now we did linearize just to calculate closed loop eigenvalues. So you're calculating closed loop eigenvalues, and you're now getting to see, of course, negative real parts. 0.2, it's still negative real part. 0.32, negative real part. And now at 0.4, for the first time now, I'm getting 0 on the real part. So now I'm going to be neutrally stable on this. So this says that just by looking at it, that 0.4 is going to be where I'm going to lose that. Here, for the fixed gains, if I do alpha 1 is 1 and alpha 3 is 2, stability is guaranteed for all epsilon below 3.2. So there's the blue one that you see right there. I'm saying I'm stable for all of that. If I pick alpha 1 is 1, alpha 3 is 1, I get stability guaranteed for all epsilon below 0.25. So what I'm showing for this is I can calculate where the bound is going to be. It's then up to you. Those are a function of the gains you're seeing on the left-hand side, epsilon star. Those are a function of the gains. So selecting those are what's going to be giving you how much stability you have for this, your stability margin. But I will caution and warn you, these are very challenging to do. For a simple problem, it takes minutes to hours. For some of the large problems we're doing, it can take weeks to be able to do this. It's very, very difficult because you have many, many of these to tune, and there is no graphical method or guidelines to be able to do that, okay? So the summary on that, real quickly, to get into now the output feedback is we stabilize a non-standard multiple timescale system. I did not make any assumptions about the roots of the fast subsystem, not all. The controllers with different speeds were addressed when I did the aircraft example. I do not have to do this with the control appearing affine. I'm not going to be touching on non-affine in this, so it can do it, but the presentation I'm doing today will be affine in the control. I do not have to have the exact knowledge of the perturbation parameter, so I'm going to say this is huge, huge step up, because now I don't have to worry about what that's going to be physically and it's not going to affect. So notice what I said. You're finding a bound on epsilon star. You know that bound, as long as you know your system is within that bound, you can be stable. You don't have to know exactly what it is. And even if you did have feedback gains, a lot of the techniques do, feedback gains with epsilon in it, you're going to have to figure out or calculate what that is much more closely to be able to get your gain. So it's nice to be able to be independent of that, okay? And then the fourth bullet, basic stuff with a good controller, I can get good response, and complete state information is required. So this is full state feedback, okay? So there's Anshu at the top left. This was her dissertation, and you're getting to see this roadmap that we have for this. If I break it into known system dynamics and uncertain system dynamics, she did the known system dynamics case. She did state feedback, not output feedback, slow state tracking, and simultaneous slow state tracking. So there's the book. This is not a shameless plug for the book at all. This is just saying, here's where to go for all the references. You know, we have papers on them too, but this is the place to go to be able to do that, okay? Now what we're doing was to go over this and say, I'm going to have known system dynamics and do the output feedback problem, okay? We're not going to go over here to uncertain system dynamics right now. I have output feedback, and this gets very challenging now. And here's why. The typical thing to do is I'm going to say I'm going to do estimation on that. So I'll maybe do some kind of a common filter, variational common filter, extended common filter, ensemble, whatever you want to have. The tricky part about this is, here's the following. My system has slow states and it's got fast states. So what do I do? Should I estimate the slow states and measure the fast states? That's one condition. How about I measure the slow states and estimate the fast states? That's another one, that's two. And then number three is to say, how about I estimate all of them and not measure all of them? So there's three different ways to do this. We've investigated all three, Dipanjan has on this. I'm going to show you just one particular case on this. And going through, it's quite involved. There's different papers we have for doing these and everything, but these are the considerations to do. It's not trivial at all to be able to work up this theory and to do it for those different combinations, okay? So what Dipanjan did, he did over here also some uncertain system dynamics. And what I mean by that, that's just going to be parametric uncertainty. So we're going to do parametric uncertainty on this, assuming that we still know the form of the dynamics on that. And while all the output feedback with slow state has been done, I'm just going to show now the simultaneous slow state and fast state tracking with parametric uncertainty in this, okay? Real briefly, I'm not going to talk about this much. I'm just going to show you that for aircraft one, nonlinear 6 DOF, you can see the different tracking types that we've done, what the approach was, what the maneuver. This is just really saying that we've done a lot on these. And to this point, we've not accounted for model uncertainties. And we're going to assume, which is in fact the case, that it can be difficult to measure angle of attack and side slope angle. Okay, so here's the example now I'm going to develop, and I'm going to show you first what we're after, which is this, and then I'm going to show you the theory that it's going to take to do this. And it's quite involved to do this, but it's very, very fun theory. So the approach will be the following. I want to do slow and fast state tracking with output feedback in the presence of uncertainties and with actuator dynamics. So this is a pretty nice set. So we'll do online parameter estimation and nonlinear state observation to do this. And I'll explain why we did that in a moment. I have more unknowns to be estimated, parameters and states, than when you get to this in some of the simple or earlier cases like I was indicating that Dipanjan did. Proving the boundness of errors and finding the bounds of the timescale parameters are challenging on this. So the solution to the approach to this is I'm going to classify the slow states as measured and unmeasured. So the assumptions are, of course, number one, all the slow states to be tracked are kinetic slow states and they are measured. Okay, so for an aircraft problem, this is pretty good to be able to do this. It's not going to be what you want to do on every single one. I'm going to assume number two, the unmeasured states are not tracked, but they have stable dynamics. okay, for that. So this is, of course, when you're going to different versions of like observability, which is the strong condition, and you go down to weaker conditions like detectability and such. So that's what this is. This is going to be that weaker condition saying, if I have states that I cannot then, estimate them and such, at least they're going to be stable for that. So not bad, to do that. Not the greatest, but not bad. An unknown parameter and unmeasured state do not appear on the same term. This is going to be because of the way we're doing the parameter estimation on this. And the dynamics of unmeasured states do not have any uncertain parameters. So automatically you're seeing what looked really good on the previous block to say simultaneous flow, slow and fast. We're now having to be very specific with it. But that's again we're doing this to direct the theory that what we're doing and where it's going. Okay, and the benefits are I can account for actuator dynamics, and I have the stability of the reduced subsystems as well as the first order system. That's going to be guaranteed. Here's what we're going to do to approach this. I'm going to go for 4 timescales, 2 for slow and fast states, 2 for slow and fast actuators, and I'm going to have multiplicative and additive uncertainties, very typical here, parameter uncertainties, and I'm going to say that not all the states are measured. When I do this, what I'm going to get control laws, which are designed over reduced order subsystems. I've already shown you what the reduced order subsystems are like. I'll use estimates of the unknown parameters in measured states. We already said we're going to do that. The update laws for the estimates will be for the unknown parameters. So we're going to develop the update laws. I'll do a nonlinear observer. We'll show where that's coming from to be able to update the measured state estimate. So we're using an observer to help the state estimates and do that. We'll have the proof of stability. I'm not going to show. We have it at several slides, but you can get that out of the papers. And then the bounds on the timescale separation parameter, those are the epsilons we have there. You can get them in closed form or solutions of inequalities. We have them. I'm not going to show those either. They're very detailed to get, but they're there. The applications, I can now do a 4 timescale aircraft with model uncertainties and without directly measuring angle of attack and side slope angle, which are both slow states, but to measure them can be very difficult. It's not always easy to do. Okay, so how are we tackling this on it? We're going to say that on the slowest time scale, I'm going to have measured and unmeasured slow states. I need to point out a difference in notation here because now you're seeing the XU that's right there. That XU is now going to say that's going to be slow unmeasured states. Okay, that's what the XU is. So change in notation from what I showed you earlier. The gammas are going to be additive uncertainties. The lambdas that are capital are going to be multiplicative uncertainties. The delta S will be a slow actuator, and then the delta F will be the fast actuator that's on this, okay? And then we'll talk about what the B matrix for the slow states. We'll talk about that, what we're doing a little bit more coming up with that. So what I'm saying now is I'm going to have some of this measured and unmeasured slow states. So there's the measured. Here's the unmeasured nonlinear function of y for that, one nonlinear function of y times the XU for the unmeasured states. And then I've got G. You're seeing then for these are going to be actuator dynamics for the slow actuators and actuator dynamics for the fast actuators for that. Okay, so the second slowest time scale will be slow actuators. And in a change from what I usually do on this, we're going to have epsilon, sigma, and rho. So epsilon will be 1 time scale parameter, perturbation parameter. This sigma that's right here, that's the second slowest time scale. That's why that's it. So this is used to be, you're used to seeing epsilon. So this is going to be sigma. Epsilon is now being used for the second fastest time scales, and then rho is being used for the fastest time scale. So one way to do it that I like better is to say epsilon sub 1, epsilon sub 2, epsilon sub 3. I like that a lot better to do that. But this case, Dipanjan chose, he wanted to show this way. The measurement now that you have typical things, slow states, fast states, slow actuator dynamic, or I should say actuator signal, fast actuator, and then some particular nonlinear function of slow, measured, and unmeasured states for that. That's just been put in for that. And again, the objective is to track. So there it is now, setting those up in the time scales. I will convert those to error coordinates. You're seeing fast and slow for that. All you're seeing on the bottom is our E dot. So typical thing to do, right? In control, say, define it in terms of error coordinates, then get the rate of the error coordinates and make sure that those things converge to 0. So there's what you're seeing. EX dot, delta S dot, EZ dot, and then delta F dot. So that's all that is, typical thing to do that. Now, here's where things get a bit interesting. We have to make a decision on this. The original work that was done on this was to say, what we all would do on this is to say, if I'm going to get estimates of the parameter, if I want to get parameter estimates and this kind of a thing, what I want to do ideally is use some type of Kalman filter. Well, what we did was working on it using process noise, measurement noise, the typical thing to do. A lot of time was spent on that, and the theory was being very, very difficult to be able to prove stability and to get bounds on the timescale parameters on this. So the decision was made after quite a bit of time doing this is we're going to go after now and use parameter updates which are typical out of the adaptive control literature. So what I'm saying is we're not saying, oh yeah, I'm going to go into I'm converting it into using adaptive control. What I'm saying here is I agree, I admit that doing it with process noise and measurement noise and doing it with Kalman filtering is the best way to go. But what I'm saying, I could do that ad hoc quite easily, not bad at all. But if I want to be rigorous about this and get the theory down and get bounds and such for this and guarantee stability, that's still difficult. You're going to see in the future work slides, that's going to be future work coming up to be able to do. So here's what we're doing for this. We're going to define B tilde is going to be in the B matrix for that. So that's going to be a 3x6 matrix. And so that's going to be control influence terms that are going to be in there. The S matrix right here, you're going to see the S, and S tilde is just the error between the estimated and then its value. This is going to be the inverse of the inertia matrix for this. So the inertias are going to be in S, the inertias inverse are, but I should say that B is also carrying, the B matrix, the B tilde is also carrying also inertias and states in it both, okay? So that's what we're doing for that. Composite Lyapunov function, we set that in. The trace elements are talked about are represented on the top. Getting the summations are just going to be when I take derivatives of the trace, it's just doing the element by element form, very typical for that. I'm doing a time derivative of that, typically thing to do, of course, because there's my composite Lyapunov function. And now you're seeing down at the bottom the parameter update laws were selected using work of Dong and Kunert in 2005. And now what I have is B hat and S hat for doing that. And the alphas that you're seeing here now, these are going to be the learning rates on those parameter updates for those who have alphas and that, and you're going to see betas come out of there too for some things. So that's what I'm saying. The parameter update laws here, there's really nothing special about those at all. They're used very, very typically in some things, but we're going to use them for our updates and do better things with them, what you can do with and putting these into timescale control for this. So the parameter update laws, you're seeing them all listed out here for doing this. The main thing to say is one component cancels an error term on doing these, and the second component will drive it, of course, to an estimated desired final state value at a certain rate. We specify those. So the results I'm going to show you, we're saying we're going to specify levels of uncertainty on these and drive particular parameters of their uncertainty to what we're doing with it. So there they are all developed out, and you see all the alphas there, alpha 1, alpha 5, alpha 6, alpha 7. There's a lot of alphas that are showing up in this. Welcome to nonlinear control. I don't have the ability to have these very, very compact compensators. I'm now getting very, very compensators with a lot of terms in it and everything there too. So there's a lot of moving parts into this. So now this is going back to what I showed you before when I showed you the full state case and the simple problem, the little second order problem for that. Same thing here. I'm going to use the Lyapunov theory on this, the Lyapunov functions, and design the controller using the same approach that I did before. I'm just going to now do one of these in each of the time scales. Okay, so like for example, on the first one, I need to design the manifold of the slow actuator so that the slow states reach the reference. I'm going to use estimates of the unknown parameters. And for this case right now, in the earlier work on this, we're going to ignore the additive uncertainty. So those are going to be punted on right now. That's why you see no gammas showing up in here. You just see the lambdas that are in there for that. So there's the reduced order model for that. I'm going to get a Lyapunov function. It's time derivative, so V dot for that. The selection of the manifold, the slow actuators, there it is. And then for the stability. So same, that's what I'm saying. We've seen this before, and that's just the way to work through that. I do it for the slow control, so the slow actuator reaches the manifold, so there's its reduced order model. You see the derivative with respect to the fast time scale. That's the prime that's right there. Lyapunov function, get V dot. In this case, I want to point out that is V dot. That's V dot in the fast time scale, so that's the derivative. There's the selection of control to be able to use for that, and then there's stability. We'll talk about the form of that slow control later on, because you can see that it has a particular form for a reason. The fast actuators manifold, same thing to be able to go through for that. And then the fast control for this. So I have to do 4 of these because I have 4 time scales. So the composite Lyapunov function is now looking like this at the top. everything in. And the point to bring your attention to is this term that's right here is going to be where the state observer comes in. So two things to note about this. These X tildes are on this. These are going to be the errors in the estimation of the unmeasured slow states, okay? You're going to put those in the Lyapunov function because I definitely want the Lyapunov function, and to have account for stability, I definitely want to have those in the Lyapunov function. So that's this new term that on the previous versions we've shown before we started doing this output feedback would not be there. So there it is. And we're going to use that to actually now design the nonlinear observer for that. So there's that new term that shows in with the error that's going to be in the estimates for that. You can see now everything's splayed out on the bottom for V, taking instead of the trace form, doing it in the summation forms for that. And now the update laws are going to be the same thing as when I had full state of this. And the time derivative will then be as you see there. So there it is, all splayed out the derivative of that. And the thing you really wanted to see now there are the terms related to state observation. So now that's what I'm going to be using for the observer, the nonlinear observer to design. And that's why that's highlighted there. Okay, now here's what's going on with this. The observer dynamics are picked as following. I'm going to have two terms that cancel out, and then a mimic term, and then the evolved term. Let's start with the evolved term. You can see that that's going to be, pardon me, that's going to be the observer gain that's right there. Very, very standard. We're all used to seeing that for like a Leuenberger observer or whatever to do that. So that term we're good to see and everything for that. The canceled terms are the following. It's going to eliminate an identical term that you have in VC dot, okay? So with this, just like you have to ensure that all parts of the terms are known for either feedback or, full state feedback or the model on this, I have to do that. So I'm going to cancel that. The mimic term that's on there is really interesting because I have X of U, that's going to be the unmeasured slow states. I have those, but I don't know what those are. Those are unknown. So what's happening is now, if you're seeing on this, you're going to see that the mimic term is going to have X hat U on that. So what you're doing is you're going to mimic and change that out there, where that mimicking term is going to replicate that term, but with the best estimate. Okay, so again, I'm using the best estimate of the U that's right here. For that, that's the mimic. The evolution will be over here, and then these terms are going to be setting up there to cancel. And because I'm doing this, again, the alphas are going to be gains that I select. So I'll just choose L diagonal, and when you do this, you get ultimate boundedness on this, okay? So let's put it into an example to show how it all comes together. And then this will be this is the final example for the presentation. The model that I'm starting with right there is nonlinear 6DOF. It's an F16. The time constants for the engine will be 1 second. That's actual. The others are going to be at 0.1. You're seeing for some of the actuators and things for that. There's the altitude and flight condition. I'm going to do a very difficult maneuver here, combined maneuver. You'll climb at 12 degrees per second pitch rate, 90-degree left turn at 18.5 degrees per second, a 90-degree right turn with a roll rate of 18.5 degrees per second, and then the velocity will be commanded to be holding at 800 feet per second at all times for that. So this is going to be a very demanding. If you can see my hands, you're going to turn left 90 degrees, turn right 90 degrees, and then pitch first when you do that. Very, very demanding. And so for any control law designed any particular way, this is going to be challenging because the coupling and addressing the coupling on this is very, very challenging. We're now for this not measuring angle of attack and side slip angle, but we're measuring the body axis velocities. So what we're saying for that is I'm measuring U, V, and W, the northeast down body axis velocities are being measured, but I'm not measuring angle of attack and side slip angle. And they're also slow states, by the way, very, very slow states. They're aerodynamic angles, okay? Now, here's the sources of the uncertainty. So this is what I'm going to pick and put into the problem based upon what I showed you before. So the inertias are going to be there, and we're going to say the initial estimates are going to be 15% below the actual value. And you remember on the estimates, I said for that, you get to specify that. So I can say I want to specify it and drive it to this value. So I'm specifying the initial inertia to be low, but I want it to be actually driving the system to be able to handle the case where it goes 5% above. So there's picking the 5%. The control derivatives are 50% below the actual values. I'm going to drive that to 5% above. And then the engine time constant, I'm going to this one pick it above what the actual time constant is, and then say take it to 5% above. So again, what you're saying is with the uncertainties that I have, I'm driving some larger, some smaller, and I'm picking them at different ones. And by the way, these numbers, as you're going to see, these are large. These are very nice amounts that you have in these. So the controller, you're going to get KX, K delta S, KZ, and K delta F on those. That's not too bad. The online parameter estimator is really, really challenging to do this. You see how many terms you have. Some of them are going to be close to 0. Most of the ones we do are going to be set to 1. The trick is finding out which ones are 1 and which ones are going to be very small, but not necessarily 0. So you see several that are 10 to the minus 13th, 10 to the minus 15th and such. And then I've got thetas that I have to do too. These are all going into the online parameter estimator. The observer gain, that's easy, 5,000 and 10,000, not too much to do for that. And then perturbations, these were put in just to try to do some perturbations in this. And I'm not too wild about these because they're just sinusoidal for this. And so not too big a deal, not very hard to deal with. Here's what the trajectory looks like. And so you're seeing, again, downrange means X, cross range is Y. You're going to take off, climb out, roll over, go over here, turn, and then turn left, or turn right, and then turn left and come out for this. On the bottom, you're getting to see the tracking on this, the reference and the actual states. Angle of attack and side slope angle are very, very nicely tracking. Velocity is not necessarily tracking too awfully well for that. Okay, so again, probably a lot more tuning would be helpful for that. It's a slow control, very slow control. The slowest on the airplane is going to be the velocity control, the throttle for that. And here you see that the commanded and actual values are going pretty nice, and the delta E that's right there. And you're seeing aileron delta A and rudder delta R. So the controls are all within bounds. The only control that's using a lot right here is going to be rudder. Rudder is going to be typically, you want plus or minus 30 degrees of deflection. And you're seeing here, these are already about 25 for this. Why is that happening? It's not because it's a bad control law. It's because this turning left, turning right at 90 degrees uses a lot of rudder to coordinate that and to keep the pointy end going forward. So it's very challenging on this. If I did a maneuver which was not nearly aggressive, rudder would be way smaller, it'd be almost 0. So this is not a flaw or a deficiency in the control law. This says the maneuver I'm doing is very challenging. You're getting to see the kinematic angles on the left. They're very well behaved. Everything is nice for there. It's hard to see on this, but the reference are the smaller dash and the actuals are the larger dash on this, on the legend for that. And the body axis angular velocity at the top, roll rate, pitch rate in the middle, yaw rate on the bottom for that. And they're doing very, very nicely for this maneuver too, okay? And then the parameter updates, all we're basically saying for these, they're going steady state, so they're converging. And a lot of these are converging to a lot of the very small values that we want on this. So that's the only takeaway from this, is to say for many, many of these that I have, they're converging pretty quickly, and they're going to nicely to the small values we want, okay? And here it is again now for different ones in there. There's a lot to be able to look at, okay? So before I get to the conclusion, I want to go back and mention something about this. If you're looking at this and wondering, what's the neat thing about this? What can I do? You can do a lot. You can gain schedule, generate a lot of linear models and gain schedule, and do this same maneuver and do it probably just as well, okay? So what is this buying you on this? What this is buying you is two things. Number one, I did not linearize anything on this, so I don't have to worry about the range of applicability of a linear model as to how wide that is, right? Because you know that there's going to be a range for how much you can handle before you get pushed out of the linear range. So I did not linearize anything. That's number one, so that's good. The second thing is there is no gain scheduling. The compensator that's designed for this and the way that's set up, no gain scheduling. So you can be basically all over the envelope on this, and you're not scheduling gains. So that's a nice feature about this. The price you're paying is the complexity is way high compared to going to a bunch of linear models and then doing gain scheduling. But I don't linearize and I don't have any gain scheduling. That's a huge improvement. And the maneuvers that I'm doing are very demanding, highly coupled. I'm in nonlinear regimes with this aircraft, high angle of attack and such, that where you'd have to schedule a whole bunch of linear models across this and everything. So that's what you're buying by doing this when you like it. So in the time remaining, when we have just a little bit of time, then I'll take questions. The conclusions are that I can use this and I can control non-standard forms using geometric singular perturbation theory. I can account for slow and fast actuator dynamics. And if you're wondering, if you're not too familiar with aircraft, very typical, you have slow and fast actuators that are widely separated in bandwidth. That's what I'm saying on this slow and fast. Bandwidth would be different on the different actuators. I can have additive and multiplicative uncertainties for parametric uncertainties on this, so I can handle those. And I did not use full state feedback on this. This was output feedback because alpha and beta were not measured. The update laws were such that the gains can cancel the error terms and the gains are used to impose first order dynamics. That's what I was saying about those dynamics you're seeing, because really what I'm doing is you're doing that with dynamic inversion. That's where you saw the G inverse on that. So I'm canceling those dynamics out and imposing and saying I want first order dynamics then on parameter estimator. Okay, not too big a deal on that and everything. So you just choose the gains to be off by several orders of magnitudes to be able to use it. But that's what we're doing for the estimator. Compositely op and off analysis was great for doing the tracking errors, manifold errors, parameter estimation errors, and state observation errors. And they're all ultimately bounded. So we proved that already. We had new bounds for this, for all the different, whether you're in closed form, solutions and inequalities, that's great. And I will say, was this done? Use of compact sets and the extreme value theorem alleviated the issue of explicit differentiating the manifolds and simplified the stability proof. As an open research issue for everybody watching this, that last bullet, we used compact sets and extreme value theorem. For that whole kind of thing. You can use explicit differentiate. There's a lot more work to be done there. We did what was expedient and got us a result. The tracking simulation results on this show that I could do this. The control derivatives were off by as much as 50%. So the terms in the control influence were in error or off, but the parameters were modeled incorrectly by 50%. That's way higher than what they are in real life. Real life, they tend to be 10 to 15%. So that was friendly for that. And I could get several of these estimated states to be very close to the actual states at all time. And that's picking the initial estimates and the one that it has to go to carefully. So that's a little bit of a weak conclusion, not too much to say there. Okay, that came out. The future work, now where's this going? I want to go back now and of course add exogenous inputs for this, great, and go into a stochastic rather than deterministic form, because the only disturbance we were putting on it before was sine waves on this, which are, poor man's disturbance for that. But it needs to go back and do an unscented Kalman filter, an ensemble Kalman filter, improve stability using stochastically op and off functions. We have been working on this for quite a while. Want to go back and do that. That's going to have to go back. It's been taking a long time to do that. So that's why we went to the parameter updates for doing that. So I'm saying the parameter updates were used to get us results to be able to get proofs on the bounds on epsilon, the time scale, and proofs on the stability. But it's not the way we wanted to do that because we had to use parameter updates. I'd rather do it this way. So that's an open thing. I want to consider the unmeasured fast states in addition to the unmeasured slow states. The example I just showed you is our best to date. And I was having 2 of the slow states were unmeasured, but all the fast were being measured. So there, as I'm saying with the observer, to update those, that's a new thing to do for that. And then Chris Leshikar, who you see on the bottom there, current PhD student, he's going to be, for his dissertation, going after the sample data, multi-rate non-scale optimal output feedback controller. So he's going to do single rate and multi-rate. And the other part of this, that diagram that you showed on the far right, I showed on the far right-hand side, that branch. Remember I said that was the uncertain system dynamic? That's what we're going to do for this. We want uncertainty in the structure of the dynamics. So if I've got higher order terms that have been neglected, or if I've had unknown dynamics, that's what we're after. A big limitation of what we're doing right now for the work that I showed you, full state feedback, and then also for the output feedback, is we're assuming we know the dynamics very accurately. There are parametric uncertainties, but what I'm saying, the structure, the form of the dynamics is known exactly. And that's the trouble with that. So we want to get away from that, of course, and get to now where I have systems with uncertain dynamics. So that's what Chris is going to be working on. We've done a lot of publications on this, and so they're on my webpage, but I can also then send you guys these. The acknowledgements, AFOSR has funded this under Fariba Faru. We appreciate that work. NASA headquarters, as part of a UREDI, University Research and Teaching Education Institute program, which doesn't exist anymore. And our part of that was called, the center was called the Texas Institute for Intelligent Nanomaterials and Structures. NSF Graduate Research Fellowship student contributed to this. DOD NDSEG Fellowship student worked on it. And then Texas A&M has the undergraduate summer research grant program. They did that. So we're appreciating all the contributions. What I'm showing you literally is from when the work started in like 2009. You're getting to see 12 years worth of work here, 12, 13 years worth of work. Okay. And I'll take questions.
Thanks a lot, John. It was a great talk. So, all right. So, to ask questions, you can unmute yourself, but not that, session is being recorded. or simply you can post your question to the chat box. Oh, Merve, you're here. I thought you have a meeting. That's why I started to take questions.
No worries. I need to leave in a minute. So.
Okay.
Thank you, John. By the way.
So, John, I will start. Are you considering extensions to, like multi-agent networks at different scales?
Very interesting. No, we had not thought about that. Okay, so it sounds like Tansel, let's collaborate on that. No, we haven't considered that. I've been so focused on having a plant that is some kind of vehicle for the most part. I've been doing that. Earlier work we did was like enzyme kinematics. So not of all of this was aircraft. Some of these have been all kinds of different things, like enzyme kinematics was one. I didn't show that. That one was not of interest to me. Anshu pursued that and did a whole bunch of theoretical work on that. There's also, this applies to plasma because plasma has slow and fast components of it. So this applies to all kinds, lasers, plasma, enzyme kinematics, anything you've got fast and slow. The tricky part about it right now is I have to model it very accurately. That's why I'm trying to get away from the uncertain dynamics, right? I'm trying to get away from exact dynamics on that. That'll open it up a lot more. But as I'm saying is we've talked with people about doing plasma. Enzyme kinematics have been done for these things. I've talked about laser. We haven't started working on the laser part yet, and there's all kinds of things. But the multi-agent, multi-system, multiple time scale multi-agent, that's neat. That'd be a neat.
Yeah, I would love to discuss. I mean, the main problem we are having, I mean, your talk, like I was discussing with Merve and one of our recent graduate students, Mariam here, as well at the audience. So, I mean, in the lab, we have, ground robots, aerial robots. Aerial robots are fast, ground robots are slow. When we try to do a mission, we need to slow down the aerial vehicle so that everything will be in coordination. And that really limits the capability of the aerial vehicles.
I agree. And this reminded me of one thing. I like the theory we've developed, but there's one part I don't like. And the part I don't like is that setting epsilon equal to 0. That was done. Tikhonov did that back in the 1940s to this. That's old to do this. And everybody does it. We do it too. It's artificial. You're doing that so you separate it into fast subsystem and slow subsystem. That's why you're doing this. The technique that needs to be done, somebody needs to get a PhD on this, is somewhere, or making contributions, is to eliminate that necessity of setting epsilon equals 0. Because what you're doing, Tansel, is exactly what you said with the air vehicles being fast and ground slow. That's what you're doing. You're separating some of that to now, right, slow it down to do that. You're artificially doing that. We'd like to keep that epsilon in the system, right? So the prime scales are represented properly rather than having to split it into the components.
No, absolutely. Also in the context of, applying singular perturbation type of theory to multi-agent systems, when you set epsilon to be 0, then actually analysis becomes infeasible because, like you basically cut the graph because of setting epsilon to 0. So you will have two not connected sets so that this, let's say, this behavior swarms cannot influence the rest. And then no proof. You got stuck. So, yeah.
And the interconnection conditions that I showed early on with the K, memory, the matrix and everything, that's because of, you have slow and fast, but that's what you're getting for setting epsilon equals to 0. That's why you have all those off-diagonal terms you have to account for. That's why they're called the interconnection conditions. A lot of that's because of doing that. If I could not have to set epsilon equals to 0, a different approach would result, which would be very nice.
Yeah, so we can chat. I can send an email. We can chat more, if you're interested.
I am.
Awesome. So, John, one more question from the audience from Liang San.
Okay.
I'm reading it to you. Nice talk, John. Thanks. I have to leave, but want to leave question, and we'll check back later in the record.
Okay.
Have you considered to leverage learning techniques to handle the challenges in multi-time scale systems?
No. And that's, again, another nice branch of that. I will say that when we started this, we intentionally did not want to go that way. We did not want to say, let's set it up as an RL problem. Let's set up, which now deep learning exists now, did not exist back then, go that way. We wanted to, at this point, and Anshu for her dissertation, she wanted to go rigorous control theory, right? She did not want to do that. So she said, I want to make as few assumptions or approximations as possible. I want to keep it nonlinear and keep everything going to the full extent of the theory. it's not, we're not there yet. We had to do a few things, but that's what I'm saying. And for Liang's question is, yeah, that can be done. That'd be a nice way to do that. And that's, I see it as a branch. You can do the rigorous way, rigorous with control theory. You can go like an RL, a learning way. But the neat thing would be to combine those, because the work that I'm doing in RL on other projects, we find out what works better is not RL by itself, but RL working with an existing controller. So there's a handshake and they help each other out. So what he's just reminded me or made me think of is we can actually now have the controller here designed as best as you can, and now use the learning to take care of some of the other loose ends and to tidy some things up and make it nicer. See what I'm saying?
Yeah.
So I would say I don't want to go and use learning only. I'd like to use learning with this. This controller can take care of some of the problems, but the learning can do some bigger stuff on it.
Absolutely. Thanks a lot, John. So we are, I should stop recording since IEEE is also posting these videos. So for any questions, your email is here. Can audience send you emails?
Yes, absolutely. Please do. And if anybody wants PDFs of the papers, you can go search for them. I'll be very happy to provide those too. They're on my website too, but I'll be happy to just get particular ones people want.
All right. So thanks a lot, John. I appreciate. So thanks everyone. So this ends today's talk.
Okay. Thank you, Dr. Yucelen, and thank you everybody for
Thank you, Dr. Valasek.
attending my talk. Appreciate it.
Have a great time, everyone. Bye.
Thank you.